Huh. So, so the mathematical statistics, effectively, we start with the first concept. What is statistic? Okay. What is statistic? And the word statistics has two different meanings. One in the popular literature, and to the statistician, it has slightly mathematical meaning. So anybody can try to explain what is the two different popular meaning? I mean, there is no right or wrong answer. Yeah.
To a statistician, it is a function of some random variables. Yeah. So I think a statistic is a function of some random variables, like say if we have a like if we have a random variable, like one statistic will be like say if we have a bunch of like IIDs, then we can consider the sum of those, like x1 plus x2 plus x3 plus dot 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 xn. That will be a statistic.
Correct. Mm-hmm. So you are saying if I have x1, x2, dot 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 xn, these are random variables, bunch of random variables that I have, then what you are saying?
Then it will be a function of that.
Okay, so you're saying it will be function of a mapping, so some here to some t, right? That's what you're trying to say, perhaps.
Yeah.
So yes, I mean, that's what the mathematical statistics it thinks about. So basically, let us take an example. So suppose I am asking everybody how many books, mathematics books you own. So the first person, and I'm assuming that number of mathematics books a person own is basically some random numbers, because in life we do not exactly assume that okay, I'll have only exactly 20 books or 30 books. I mean, that never happens. If we like a book, we just buy, and our likings and dislikings are some sort of random behavior. So suppose you have a data points or the first person is saying, okay, I have 22 books. Another person is saying, okay, I have 13 books. Another person is saying, okay, I have, maybe 27 mathematics books. So that means, are these random variables? These 22, 13, 27, these numbers?
These are the value of the function at these random variables. Right?
Correct. So they are realizations of the random variables, right? So this is just one realization of the random variable. It could have, the first random variable could have been 21 or 23 as well. It happens to, we have seen 22. Okay. So this is the realization. And so that's why we typically in statistics, what we use two notation. One for the random variable, x stands for denoting a random variable, and small x typically we use for realization of random variable. Realization of random variable. Okay. Now, Now, so what we generally happen, if you look into that suppose we have asked 30 people or maybe 20 people. So it's a vector. Suppose the last value is maybe 32 or something. So suppose we have asked 20 people randomly chosen from CMI community that how many mathematics books they have, and they have responded to the numbers. Okay, and so it will be my data set can be viewed as a size n, in our example n equal to 20. Okay, now effectively whatever information that we have this information in n dimension, I can think of. But so my entire information is in n dimension, and that actually does not help us much. So what we do then, we said, okay, can we come up with some summary which gives up some idea? So what we do, we said, okay, can you tell me the average? Okay. So average gives us some decent idea about, on an average, how many books this group of students and faculty are holding as their own mathematics books. So what we do, the average is typically what we do, we sum them up, x1 plus x2 plus dot 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 xn and divided by n. So what we do here, we took this n dimension object, we made an operation on that n dimension object, and we came up with a single number. Okay, so my n dimensional object got projected in one dimension. Okay, so n dimension object were getting projected into one dimension. So technically I am reducing the dimension to understand the to summarize, to grasp certain information. So two things are happening. First, in this case, actually it is a two operation. If you look into the average, first we are doing sum, s is summation xi, and then we are dividing it by the n. So I can say there are s itself contains certain information about from the data set, and x bar also contains certain information about the data set. Question is, so that means s, x bar, these are all s, x bar, these are all what we call statistic. Okay, these are all statistic. But can we, and then there is another concept called estimator. Okay. So I to get to the next. Then there is another concept called estimator. Okay. So now we have a big data. Data is x1 to xn, and then this is which is in n dimension. And then we have some statistics, s, is summation xi equal to 1 to n. And then we have x bar. X bar is s by n. The question is, these are statistic in one dimension. Statistic in one dimension. So I'm compressing information from n dimension to one dimension. Remember that. And then there is a slight difference between statistic and estimator. Can anybody tell me what is the difference between statistic and estimator? It's a subtle difference.
So estimators are a subset of statistics.
Okay. What will make it a particular? So you are saying estimators are also statistics. That means
Yes, but all statistics are not estimators.
Estimators. But what makes a statistic an estimator?
They estimate population parameters.
Correct. Very good. So that means I'm assuming when I'm saying x1, x2, xn are random variable. Very good. When I'm saying a random variable, I'm assuming there is a distribution behind underlying distribution. There is a probability distribution from which these data points are coming. These random variables are getting generated. Okay. And that distribution will have certain parameters. When I'm saying parameters, typically it will be mean, variance, or some of the distributed rate, scale, different parameters can happen, or like, proportion. So these are the typical parameters of a probability distribution. So if suppose I'm interested in population mean, suppose theta is equal to population mean. I'm interested in population mean, right? Generally we denote it with mu. And then if we can generally what we do, we try to estimate population mean by either average. Any other thing you use? Any other estimator for population mean? There is something called trim mean also. Okay, I'll talk about it. It's called alpha. It's called trim mean. Can I leave it as an assignment to figure it out? What is trim mean? I'll not say, you just figure it out, trim mean. Okay, so anyway, these are the typical estimator for population mean. Can I use S for estimating population mean? The answer is no. Why? Because we cannot directly use that. We have to divide sample. So S is also a statistic. X bar is also a statistic, but we cannot use S to estimate mu or the population mean. We have to make some, divide it by n, and then we can use it as a thing. So that means some statistics which we can use for estimating population parameter are called estimator. Okay. But whether it's statistic or population estimator, no matter what you are using, what happens is, if you end of the day, you are in n dimension and you're doing certain operation on these n dimension, and you projecting your number in one dimension, and you're trying to make some sense out of this. In this process, you may lose information. So it is called, typically what we are doing, typically this type of method is called dimension reduction. Dimension reduction. Typically dimension reduction is a much heavier concept, but this is the simplest example of what we call dimension reduction. So my my entire data is on an n dimension because I have I am seeing it as a vector, okay, from a matrix algebra point of view. Then what I'm doing a operation on that and putting the entire n dimension object into one dimension. So I'm reducing the dimension. While reducing the dimension, we may lose some information. While reducing the dimension, we may lose some information. So what should we do now? Any idea? So we should, when we are doing dimension reduction, so when we are reducing the dimension, a key thing is we should be careful about information loss, possible information loss. Acha, one more thing, students often get confused. So far, I am only considering one variable. Okay, so like it's like, if the analogy with the calculus or matrix algebra will be, with calculus it will be like one variable calculus, or with a matrix algebra it will be just one vector. If you have a data set which has say n rows and p columns, then each column suppose represent a certain variable, then I'm just considering one column as like as my variable, and I have x1, x2, xn, each cell values of that column as my numbers, or I'm considering these x1, x2, xn's are coming from some distributions. Okay, so I just mentioned that because later when we will see that here I'm reducing dimension with respect to the sample size. Later we will see when we will do the dimension reduction, we will have to reduce the dimension not only from the concept of sample size, we also may have to reduce the dimension with respect to the number of variables that we have in hand. Because right now, as if we have one sample, one variable, and there are a lot of samples. Okay, and the sample size is increasing sample size, and we want to reduce that thing. So in that sense, we are reducing the dimension. In that sense, a later stage, we will figure out that, okay, not only our sample size is increasing, our number of variables are also increasing. I mean, I'm seeing, like, if you go to, if you are working in a biological space or, a medical school, and if somebody is working with genetics data, you could easily have variables in your data could be crossing 10,000 or 15,000. how, so naturally, so you have, if you have 15,000 variables, you would like, somehow you would like to reduce that dimension in certain way. So when we are reducing dimension, it could be two different ways. One, it could be sample size, from the perspective of sample size. Here the sample size, and standard convention is we denote sample size with n and number of variables with the p. So it could be both. A later stage, we will see that we have to reduce this dimension reduction. More complicated problem is when we have to do the dimension reduction in with more number of variables. So right now I am introducing you the concept on sample size perspective. It's comparatively much easier. So when we are reducing this dimension, we should be careful about this possible information loss. Next question is that, okay, fine, this is, we will keep that in our mind. So what would be the best thing in that case? That case, that if we reduce the, if we come up with a statistic P of X, so where is sufficient if it contains all information about theta that is there in X tilde. So where X tilde is my samples, X1, X2, Xn. So this is a very generic concept of what is sufficient statistic. Okay. Okay. Up to this, anybody have any doubt? So we want to come up with a statistic which will contain, so basically all the information that we already have in the X tilde. Okay. So this is what the basic concept of statistic is. Now, this entire concept of sufficient statistics was, the entire concept of sufficient statistic was developed by the father of modern statistics called R.A. Fisher. He was basically a nutcase. He was a racist person. A few days back, his name was erased from Oxford University's wall. So, but anyway, that's a different story. Fisher came up with, this concept of sufficiency, that, okay, and he gave a very weird kind of definition, and it took quite a bit of, generally it takes quite a bit of time to understand the sufficiency principle the way Fisher did. And later, much later, when I was doing PhD, one of my professor, he presented the concept of sufficiency from a very different angle, using Fisher's another concept called Fischers Information. And that definition I found much more easy and easy to grasp. So I'll tell you the book. The book name is probability and statistical inference. Probability and statistical inference by Professor Nitish Mukhopadhyay. His book is, I think it was Marcel Decker. I'll check if we can order a copy of this for CMI library. And so what I'm thinking is, first I will introduce this concept from Professor Nitish Mukhopadhyay's concept from book, and then I will move to Kasseler-Berger, the way Fisher presented the concept of sufficient statistics. I found Fisher's concept, and to understand Fisher's concept is very difficult. It takes a lot of reading and a lot of thinking. Comparatively, I found Nitish Mukhopadhyay's presentation of concept of sufficient statistic is much more easy and easy to understand the concept. So he comes from the concept called information. So because if you look into the generic concept, it's saying that it contains all information. So first we have to understand what Fisher tried to mean by information. So Fisher defined information in a very particular way. Okay, so let's go to first what is called Fisher's information. Fisher's information. Now, Fisher's information about theta. So what Fisher is saying, that suppose X is a random variable which follow a distribution with certain P density PF with a parameter theta. Now the information it contains is I, the information about theta that is there in X, that is what it's talking about, is equal to expected value of del theta log of f x theta whole square. He also showed that the same thing you can show in this way also. The expected value of this del theta 2 log of f theta x. So this is what Fisher's information is. Now, if you look into this definition on this one, effectively it is saying that curvature of the density, expected density, is the information. So what it mean by curvature of the expected density? So basically, if you have something like this, your theta is your, so first of all, you just looking at the f log of f theta is, it's sort of bringing the information of likelihood. And if you suppose this is the theta, and if your density or this log f theta x is behaving like this, or then it has certain degree of curvature information here. Okay, curvature is very sharper actually here, whereas if I have another thing about theta, so here what we are seeing that the curvature is much more flatter behavior. So I would expect that in this one, I have more information, whereas here I have comparatively less information about theta. So that is what Fisher is trying to capture by means of information about theta. Okay, so that is the motivation of Fisher's information about theta.
So I have one small question.
Yeah.
So here, so is the assumption that more curvature implies more information, less curvature implies less information?
Looks like, I mean, that is my understanding, to be honest. I mean, I have not seen exactly the interpretation. Everywhere it is just written, okay, here is the Fisher's information, Fisher, that's how Fisher defined it. So I came up with my interpretation, and this looks like that is what he meant to capture by this, that on an average, what is the curvature. That is what he tried to capture.
So in some sense, curvature is sort of measure of the information.
Correct. Okay. Correct. That is something he probably tries to capture, because this likelihood is around the theta, how the curvature is changing. That will contain because if the curvature is changing very sharply, that will means that has a lot of information about theta, because most of the mass is around theta. Whereas if the curvature is not changing very sharply, it's flat, that means it's all over, the x is all over, it's not very close to theta, and that means that will indicate that it has lesser information. That is my understanding, to be honest, after. Okay.
Excuse me, sir.
Yeah.
Sir, so over here, the definition given inside, let's say the function f is coming from normal distribution. So theta would comprise of mu and sigma both, right?
Okay, good. So here I am doing it for only mu, and as if sigma it's for one parameter. For multi-parameter information, it will be effectively, if it is two parameter, then it will be the information matrix. It will be information matrix, and it will be a 2x2 matrix.
Okay.
If it is p parameter distribution, then it will be a p parameter matrix. Yes. Okay. Good question.
Also, when we say Fisher's information about theta, it's a constant information about a particular type of distribution. Given the definition, I mean, so when we say Ix of theta, so what information are we meaning about? Like,
so I have just one, as if I have one sample. If you think of just one sample from an unknown distribution, and then how you capture it, how you present it. the information. So even one sample will contain some information. Okay, so that is the way it is being defined.
Given
Next,
that we assume a particular distribution it's coming from.
now if you're assuming it is coming from a distribution, then you will be able to have a mathematically closed form. If you can solve this differentiation, and expectation means it's an integration.
Yes.
Integration with respect to f. So you have to solve
Yes.
that integration with respect to f. If you have an analytical closed form solution, then you will know exact form of the Fischers information for that particular distribution. Okay.
Okay.
So basically, if you assume it is say normal mu1 in this case, then you first of all you put a density of normal mu1 here. You have to take double derivative of log of density. Then you have to integrate out with respect to the PDF of normal mu1, and whatever you get, put a minus sign there. That will be your Fisher information for normal mu1.
Okay.
So you can do it separately for each of the distribution.
So the curvature we're talking about is the curvature of the distribution itself.
Correct. So that's a good question. Now, my understanding is it is not the curvature of the distribution itself. It is actually coming from the concept of likelihood. That theta, if I have the theta at a different values, then likelihood will behave differently. Okay. So, and that, because if you look at the definition, it is taking a differentiation with respect to theta. So that means my x-axis is theta. It's different values of theta, because once I observe the x, then I can't do anything. It's just constant, right? And then basically what I'm thinking is, all right, I have a constant x now, and given the x will behave like a constant, but then you see that, okay, how the curvature is with respect to the theta, how this curvature is changing. And then a weird thing that, not weird, rather, it's an interesting thing, because then Fisher is taking expectation with respect to fx. So that expectation is with respect to the variable, random variable. That if the x changes, on an average, how this curvature will change. So that is a very interesting concept in that sense.
Okay, so
yeah,
basically changing of x might affect the distribution that it comes from.
Of course.
And that distribution's maximum likelihood function, while being optimized, if it has more slope around it, then it will have more Fisher information.
Correct.
Okay.
Correct. And then you are taking on an average. When I'm saying expectation, that means it's like on an average, if my x keeps changing, or it's like, so Fisher comes from a very remember that, I mean, Fisher comes from a very classical physics point of view. His point I was always, like if you do a thought experiment that, okay, I have drawn a random sample on my own, and then you drew another random sample independently of yourself, from independent of me, and your measure of theta and my measure of theta will be slightly different because it's a random sample. But so in order to capture, but how much information you have and how much information I have. So then you can think of, well, I can calculate this curvature with respect to, I can calculate this curvature, but that means then I have a curvature, you have a curvature, but what is the correct information? Then he's saying that, okay, let's take the average of these curvatures. So that is where this expectation with respect to the if thing is coming.
Sir, I have a doubt.
Yeah.
No, sir, the expectation is just the average of del theta means the slope of every theta 1, theta 2, theta 3, and so on. We are taking the average of those values.
No. So here I'm taking the average with respect to, okay, let me write down the entire information thing, then it will be much easy for you. So when I'm saying that this negative expectation of if del 2 del theta 2 f of theta x, when I'm saying this, it means effectively, it means I'm taking integration over chi, okay, del 2 del theta 2 f theta x f theta x dx. This is the exact thing that I'm talking about. So this part I'm taking the differentiation with respect to theta, and then I'm taking, but I'm doing the integration with respect to the x. So you have to be careful there. So that is where that is what it captures the entire thing. Okay.
So,
Yeah.
sir, I have another doubt. So, I am not able to understand that what I theta basically captures. Like, if we have one sample only, and we get a value for I theta, so is it the percentage of the information captured by that sample, or what it is basically?
No, it's not even percentage of information. We are talking about what is information, how you define information. So here Fisher is defining information.
So, sir, there is no unit to this information. Like,
No.
like if we have, like if we have to compare two different information, so the one which is greater would be better.
I'll come to that. I'll come to that. I'm not. You are already in the comparing of the information. I'm just defining information. Once we agree to this understanding of the concept of information, then we will go and say, okay, can we compare the informations? Okay.
So here I think so.
Okay.
Ix theta is measuring how much information X carries about theta.
That's it. That's it.
So it's a unitless quantity.
It's a unitless quantity. It is just saying that, okay, this is my definition of information. I'm defining it. Once we agree to this, then next level is, okay, how much can we compare this with that and all these things. That I'm going to discuss right away. Okay.
Okay, sir. So, ma'am, could you repeat the statement you gave, like how much information X is containing about?
X carries about theta.
Okay.
So this will be some number, and my guess is that you will, compare these numbers for different variables. Maybe, I don't know.
Yeah, typically it will be some function of theta.
Sir, then if we consider a function like a Dirac delta function, then it should contain complete information about theta, right?
I'm not sure your point. I have understood your point.
I mean, like if we have a distribution that is like 1 at one particular point for x and 0 in 0 everywhere else, so that contains like, so that is, so theta will be like that one point only, no?
Correct. Yeah. Yeah, that's trivial in
Yeah.
that case.
So I'm just trying to understand how
in that case, I'm
we
not
use
sure
this.
even this Fisher information will be defined because
Okay.
because you cannot take the even differentiation, nah?
Yeah.
Right? If you are saying that theta equal to 1, I have the 100% probability mass and 0 everywhere else, that I cannot even take a differentiation on that because you know everything about theta, that means. And I cannot, at least this definition of information will not be valid in that example that you are talking about. Because you cannot even differentiate at that point. It's a complete discontinuous point.
Right. So the graph is like a spike.
Correct.
Graph of theta is like a spike at theta.
At a spike at a particular point and 0 everywhere. So you cannot differentiate at that particular point. So, okay, now we have said, all right, this is my single observation. Let us now move on to what will happen if I have n many samples. So the way it is defined is like x1, x2, xn are IID, independent and identically distributed random variables with some density f theta x. Okay. Now we also agreed that that information for ix1 theta is equal to is e theta. So negative e theta del theta 2 del theta 2 log of f of x1 theta. Okay. Let me denote this vector as x tilde. This is my data set. Okay. This is x1 to xn is my data set. I'm denoting it as a x tilde. Then the result is, one can show, I'm not going to the proof, I'm just stating the result, that information of the entire data set is n times ix1 theta. This is a result under two assumptions. One is that your data set is following IID. This is a very important assumption from some density. And second is you are assuming this is your information, Fisher information. In that case, you can show the total Fisher information for the data set is just nothing but n times of Fisher information for x1. And so this is an important result. You can prove this result. Actually, President Nitish Mukherjee's book, he have provided the proof. And this is going to be a very important result that we are going to use again and again and going to understand the concept of sufficiency. Then,
sorry, can I interrupt?
Yeah.
So does this seems to say that it is enough to know the information about theta contained in x1, just the first variable? What it means?
If IID, if you assume these are IIDs.
Okay.
If you assume this, then yes, then this result work. But if you don't know if they're IIDs, then this result will not hold. Then at least I remember, I think we were asked to prove that they're independent, not identical. I think in that case, it will be like ix1 theta plus ix2 theta plus ixn theta. So it will be like, I think, as if I'm not wrong, if you drop the identical assumption but keep the independence assumption, then I think it will be something like this, if I'm not majorly mistaken. Summation information about ixi of theta.
Okay.
I
So in
think
case of
I know
IID,
that.
the thing is much
Correct.
simplified.
Correct. Just sum of the thing. I think the result is correct. What I'm quoting. So basically, if I'm saying identical, that means x1, x2, xn, they are identical random variable. They have exactly identical distribution. Then ix1 theta and ix2 theta are same, basically, I'm saying. If they're identical, then I of x1 theta is same as I of x2 theta. Sorry.
So everything really depends on this distribution. If the distributions are identical, then the information the variables carry will be identical.
Same information, exactly. So that's why it's just n times. Basically, you just ix1 theta plus ix equal to ix2 theta equal to ix3 theta. So this will be basically n times of ix1 theta. But independence is very important because of the independence, many things get cancelled and makes the life simpler. But if the things are not independent, they're dependent, then I don't think any mathematically closed form result for information exists. At least not that I am aware of. Maybe there are. In a standard textbook, mathematical statistics textbook does not discuss beyond independence.
Okay, thanks. Yeah, that was nice.
Yeah.
So is there any,
yeah,
is there any finite range of values that ix of theta takes? Else,
finite range of?
Is there any finite range of numerical values that information content of theta takes? Because else we won't be able to say that
So information is
good
always
we are.
function of theta. Any information will be always, the way it is defined, if you look into the definition, it will be some function of theta. Right. Now in classical statistics, it is always believed theta is constant. Okay. Theta is constant. So if you if you plug it in, then the information is also some finite information is there if G is bounded.
Okay.
So
yeah.
So one thing here, like you said, it's some function of theta. So if say ix1 theta comes out to be 2/3 theta, so does that mean that x1 gives 2/3 information about theta?
No. It's just a functional form that has come. It will be, if you can come up with certain kind of interpretation, fine. But I would be, I would be careful to making such interpretation. Interestingly, most of the popular for the popular distributions like normal, Gaussian, binomial, Poisson, there is an interpretation. When we will do the examples, we will calculate the Fisher information for binomial, at least for the binomial Poisson Gaussian, at least for the one parameter Gaussian. And we will see that these Fisher information does have interesting interpretations. But we will come to that maybe in the next discussion. Okay.
Hello, sir. Sir, can we say that TX is a sufficient statistic if information of say if I of TX theta is equals to I of X tilde theta?
Yes, I think you are right on the money, and I'll going to discuss that thing. You are right on the money. Yes. And I'll tell you. So before jumping into, I mean, I think you got it already. But let me just tell you one thing. So if x1, x2, xn is following some distribution, say IID, to make our life simpler, if theta x, okay, then what is my statistic? My statistic is T of x tilde is, let us call it to just T. It's an operation on the random variables. So I can say my T is also a random variable, correct? So T will also have its own distribution. Let's call it G theta T. Are you okay with me? Huh? It has
Yes,
a
sir.
special name. Do you know what is that special name? This distribution has a special name. Any idea? Okay. The name is called sampling distribution. Okay. How many statistics students are now breaking their head? So example is, if x1 to xn are IID, normal, theta, or mu sigma square, and if I say my x bar is my statistic, x bar we follow, we say normal mu sigma square by n. This distribution has a special name. It's called sampling distribution of sampling mean. I hope you should have remembered that. Probably you have forgot it. All right, let me continue. I'm almost done. I'll not hold you out anymore. So last thing. So now if I have these things x1 to xn follow f theta x, these are IID, x tilde, then we figure out that for this, the Fisher information for x tilde theta turns out to be n times I of x1 theta, and then we figure out, okay, I have a tx equal to t, which has its own sampling distribution g theta t. So can I say that since it is a distribution, so it has its own Fisher information? So I can compute the Fisher information of I tx of theta, whatever that might be. I can always compute that. That will be negative expected value. I will take this expectation with respect to G, not with respect to F, because this is the thing. And then del 2 del theta 2 log of G theta t. This is the Fisher information of the sampling distribution. Now we can say that I x tilde theta is always greater than equal to I t of theta for all theta in its entire parameter space. Can I say that? Because remember that what is Tx? Tx is function on x tilde. Under any circumstances, actually, this is actually a theorem, okay? This is theorem, you can prove it. Under any circumstances, the Fisher information that you have in Tx tilde will not cross the Fisher information that you have in x tilde itself. That is what it's talking about. So that means if I can show that my Fisher information, total Fisher information in Ix tilde theta equal to I of statistics, the Fisher information is statistics, then I can say that my statistic, which is in the say one dimension, contains all the information that we have in x tilde, which is in the n dimension. Then T is called sufficient statistic. Okay, anybody have any doubt?
Sir, my doubt may be a little trivial. So now this T of x is a function of the random variables. So is it necessary that it also have the same parameter? Like if you take sum of normal IIDs, it will have a mean, like it will follow normal distribution, but its mean will be
no. It can follow some completely different thing. For example, if you take sample standard deviation, okay, sample standard deviation follows scaled chi-square distribution. Okay, it has nothing to do with normality. So
basically, this theta and this theta, the IT of theta and Ix tilde of theta are
the same theta. No, they are the same theta. Remember that they are the same theta. Okay. But distribution may be very different. Sampling distribution could be very different from the population distribution. Because you are doing an operation on this x1, x2, xn. After doing that operation, the distribution can change. Original distribution is, the population distribution is maybe something normal. And you are, suppose you decide, okay, instead of taking the average, I'll take the sum of squares of average. Like, I'll just square each of them, x1 square plus x2 square plus xn square, and then I will sum them up and, I'll take average. Or I'll just take the sum of the squares. Then the distribution will be some kind of scaled chi-square distribution or scaled comma distribution. Okay. Because you are doing an operation with, and after that operation, your Tx could have a very different distribution. But still, that T contains information about theta.
Yes, sir. Now I understand. Yeah.
That is what we are trying to say. That after that transformation, it might happen the information, you have lose some information. In that case, Ix tilde theta will be greater than equal to It of theta. But if you can mathematically show that, okay, my Ix tilde is equal to exactly It of theta, then I can say that, okay, T is sufficient statistic, sufficient in the sense it has not lost any information while doing that operation, while doing that mathematical operation. And not losing information, you will see a consistent theme in the dimension reduction technique. Any kind of, eventually, I think your DMML class has started. where DML class, Professor Madhavan will teach is principal component analysis. I think Professor Kavita, you are teaching SVD also probably as a part of linear algebra. These are all dimension reduction technique, and all this dimension reduction technique, you will see a consistent theme that while you're reducing the dimension, you should try to contain the information as much as possible. And when you are saying that I am trying to contain the information as much as possible, the concept information becomes very important. And with respect to the problem, your information, the concept of information will be slightly, you have to define your concept of information. So here I am defining concept of information with respect to Fischers information. Now you can come and say that, well, what about entropy? Entropy is another definition of information. Should I try it out? Why not? I have not seen the mathematics on, defining a statistic is sufficient with respect to the entropy information. I have maybe some attempt has been done, but in a standard statistics textbook, everything is done with respect to Fisher information. But defining a particular information with respect to the problem and then dimension reduction with respect to the information, and while after that you have to show that after doing that operation and doing that dimension reduction, you have not lose much information, or even if you have lost, the loss will be bounded, means you can give an upper bound of the loss that you have to ensure. Okay, so I think that is what today's main take home message.
Can this I theta, excuse me, sir?
Yeah.
So can this I theta turn out to be a constant function? And in that case, what does it mean?
I theta will be a constant function from a classical
independent of theta.
I theta will never be independent of theta.
Like for some case, just double derivative inside.
Okay.
Turns out.
Got it.
Yeah.
Suppose I t theta, that ix tilde will always be some function of theta because it contains the information about the theta. But it might happen it theta is free of theta. Suppose free of theta. If that happens, that means t does not contain any information about theta. So that means t is not a very useful statistic. I would not like to use that statistic for my for my analysis. If my target parameter is theta, and it turns out the statistics that I am using is free of theta. Okay, so that means effectively the t does not contain any information about theta. It's basically something like that. It's your theta is somewhere here, and maybe it's just a constant. Like this is what is. So there is no curvature. Almost curvature is 0. Or so that's what it is talking about.
Okay.
So it doesn't contain any information about theta. I would not like to use this statistic at all. Okay, it's a good question. Any other question?
So in practical purposes, while doing projects, do we use Fisher information?
In practical purpose, if you're doing a project, do you need no, not really. Not really. Okay, let me put it in this way. 99% of time you will find a project which you can deliver with existing tool and technique. There could be 1% of time where you might find problem which does not fit into a standard textbook, off-the-shelf tools, technique, and textbook analysis. That time you may need to develop a new algorithm or new statistical technique. At that time, these concepts might help you to keep, okay, I'm developing this algorithm. How do I make sure that it is not losing informations and stuff like that? So this is the concept of sufficiency. The sufficiency is telling us basically that when you are doing a data dimension reduction, you should not lose your information. So if you have to develop tomorrow or in future, you are trying to develop an algorithm which effectively comes into some kind of dimension reduction, whether it's a sample size or variable number of variables, whatever kind of dimension reduction, and turns out to be you are doing a new kind of developing new methodology or new algorithm. What require is, in that case, you have to keep in your mind that if you can show that these methods or these algorithms has this kind of property, then I think people do appreciate that, and definitely academic community, you will be much more appreciated.
Okay.
Okay. Any other question?
Sir, where will you be sharing this recording?
Yeah. I'll share the recording, and I'll try to share the notes as well. So this iPad is new thing to me, so I have to figure out how to save these things as a PDF and share it. But as soon as I come, I'll share it with you guys. Maybe I'll just create another Moodle page on mathematical statistics, and then it will be much easier to share with you all of you guys. I'll add you in that page. Okay, all. Thank you very much. So I think it's time for lunch. It's really hungry. Thank you all. So see you next Saturday, same time. Okay.
Thanks.
Thank you, sir.
Thanks. Thank you.
Thank you so